Your application state contains sensitive data, but how do you keep it secure when persisting to databases or storage? We'll implement end-to-end encryption for your LangGraph workflows with just 2 lines of code. You'll see how to wrap any checkpointer with AES encryption, ensuring all persisted state remains confidential while maintaining full functionality for time travel, memory, and fault tolerance.
From LangGraph, checkpoint, CERD, encrypted import encrypted serializer. From LangGraph, checkpoint, Postgres import Postgres saver. CERD equals encrypted serializer. From PyCryptodome AES. Checkpointer equals Postgres saver. From con string PostgreSQL // CERD equals CERD. Checkpointer setup.
This demonstrates the persistent state pattern with encryption, combining durable execution with data protection. The concept involves saving application state at discrete steps checkpoints to enable recovery, inspection, and time travel debugging, while encryption ensures sensitive data remains secure at rest. What makes this distinctive is the separation between the persistence mechanism Postgres and the serialization layer encrypted serializer, allowing independent scaling of storage and security requirements. The pattern works by intercepting state transitions and writing immutable snapshots to a durable store, with each checkpoint capturing the complete application context at that moment. Encryption happens transparently during serialization, so the persistence layer only handles encrypted blobs without needing security awareness. This design enables features like fault tolerance resuming from last good state, audit trails inspecting historical states, and secure multi-tenant deployments isolated encrypted data. This approach matters because it solves the dual challenges of reliability and confidentiality in stateful applications. You use this when building systems requiring both operational resilience, like workflow engines or chatbots, and data protection handling PII or proprietary logic. The trade-off is slightly higher latency from encryption decryption, but the alternative, plaintext persistence or manual state reconstruction, introduces far greater risks and complexity. Let's break it down line by line.
From LangGraph, checkpoint, CERD, encrypted import encrypted serializer.
Imports encrypted serializer, a secure serialization component for checkpoint data. This handles encryption decryption of state before storage, preventing exposure of sensitive information in the database.
From LangGraph, checkpoint, Postgres import Postgres saver.
Imports Postgres saver, a persistence layer that stores checkpoints in PostgreSQL. This enables durable state management across process restarts, critical for long-running workflows.
CERD equals encrypted serializer. From PyCryptodome AES.
Creates an encrypted serializer using PyCryptodome's AES implementation. This ensures all checkpoint data is encrypted before storage, preventing exposure of sensitive information in the database. The serializer handles both encryption on write and decryption on read operations.
Checkpointer equals Postgres saver. From con string PostgreSQL // CERD equals CERD.
This code initializes a Postgres saver with AES encryption for secure checkpoint storage using the provided PostgreSQL connection string. The setup call required on first use ensures the database schema is properly initialized, while the encrypted serializer, CERD, handles data encryption decryption at rest. The checkpointer is then ready for use with LangGraph's persistent state management.
Checkpointer setup.
Initializes the PostgreSQL schema required for checkpoint storage. Must be called once before any operations to ensure the necessary tables exist for storing thread states and checkpoints. LangGraph checkpoint integration. Encrypted persistence bridges state management with production-grade storage. The encrypted serializer, and Postgres Saver combination demonstrates how LangGraph handles secure, durable state persistence, where serialization CERD encrypts data before storage, while the checkpointer manages thread continuity and recovery. Encryption via from PyCryptodome AES requires the PyCryptodome dependency, which isn't always explicit in error messages when missing. Always call setup on first-time Postgres Saver initialization to ensure schema compatibility before graph execution.
The connection that encrypts nothing secures every secret